send everybody an email that has a rotated Smith chart on it, hopefully. Now, is everybody able to access your quiz grades? I want to make sure that you can see. Okay, good. All right, so. So today we're talking about going to chapter 10, microwaves, and on Friday I mentioned about what we're really talking about is George Ward and causing line with stuff. But here's what my plans are for today. I'm going to go over some of the basics of characteristic impedance of these things, for the dimensions of width and height and epsilon relative. I'm going to tell you, these kind of formulas, I don't expect you to remember. I'm going to expose you to them because you should see them at least one time, and I'll discuss them. And then we'll get into the rotated Smith charts, which really is where I want to go today. But first of all, with microwave engineering, what you're really talking about is something where you have a board as such that has a given height on the board. It has some epsilon relative, permittivity, usually somewhere between 2 and 4, maybe 5. But it's not real high. And then on top of this board, you're going to have things that have a line width. This is going to be made of copper. It's all copper. And you're going to have a certain thickness to it. Now, the back of this board is also grounded. So this is like copper clad. And I told you last time, you basically get rid of the copper you don't want. Use that as basically a strip line that will have a characteristic impedance. Do y'all follow me in that? Just like a waveguide. Now, but these things, they're not waveguides, they're transmission lines. So think transmission line, not waveguide. So when you have this, there's something that they talk about. The first thing is the effective dielectric constant. You have dielectric on one side, but not on the other. So they talk about the effective dielectric constant. And it's 1 plus epsilon relative over 2. Actually, there's probably several different ways to write this same equation that are about the same. And it's plus epsilon relative minus 1 over, and then over 2, and it's the square root of 1 plus 12 W over H. I'm sorry, H over W. And I got to tell you something about this. You look at that equation, that didn't come from Maxwell's equations. That didn't come from fundamental physics. What it is something where people have found out in industry an approximate formula to use to get this value that we're going to use in other formulas. You all with me? So again, this is just one of those things. They've done some curve fitting and they try to find a mathematical formula that gives a good approximation. This is in the book, but again, you don't have to memorize this, just for exposure purposes. Next, after that, we talk about this is important, but the characteristic impedance itself is the characteristic impedance between this line and the ground. Now, yeah.
What's over omega? The denominator there?
From H over W.
This is H over W. I mean, this is in the book. Can anybody tell me where that formula is in the book? If you get your books out. It's in the beginning of chapter 10. And again, I want to say one thing. If you look online, you're going to see a variety of other formulas that do the same thing. They're not the same form. Sometimes they're polynomials. Doesn't matter.
544.
Page 544. You can just take a look in the book. You don't have to write this down. Just pay attention, because I got to make some comments about this. So what we're really talking about, we're creating transmission lines on these boards. That's really it. They're not waveguides, they're transmission lines. And when you talk about this characteristic impedance, the first one is going to be, and here it uses 60 over the square root of epsilon effective. And this is a variety of these. I know because I did a paper on this years ago, and I'll explain that in a second. And I realized just how much industry has on approximate formulas for this stuff. And this is in ohms, and this is for W over H less than 1. Then you get another one. This is the characteristic impedance. And this is gonna be 120 pi. This is really 8 and naught here, 120 pi ohms. And that's gonna be over the square root of the effective permittivity. And then you get a wild formula. It's W over H plus 1.393 plus the log, or plus really 0.667 times the natural log of W over H plus, I'm going to say, .41. Yeah. All right, so this is for W over H greater than 1. Now, here's some comment on this, though. These are, again, approximate formulas. They're not exact. Here's the approximate characteristic impedance of a line for different ratios of width to height. Generally speaking, the width on these lines is probably less than the height. Generally speaking, not always the case, but usually it is. Because this is fairly, not thick, but it's thicker. These line widths are going to be small. Not all the time, but generally. I don't have a lot of experience with these formulas, but here's how I got into this. Bless you. Years ago, I was doing some modeling work for these type of microstrip lines. And here's one of the problems. When this right here gets close to the edge, right here, all of a sudden the characteristic impedance starts changing. And a lot of times you want to get something near that edge because you want to make the best use of the space. It's called the footprint that you have to work with. It's really the amount of board. They want to put every device you can on there, and you want the smallest possible size. But these formulas work only when you're in the center of the board. As you get close to the edge, things change. So what we did, we went through and we did modeling for all sorts of thicknesses, all sorts of epsilon relatives, and all sorts of widths. And we came up with a family of curves that we developed that approximated the actual, both the characteristic impedance here, the effective permittivity, and really, I mean, the real thing is the characteristic impedance. So, there were design formulas when we published this thing. But I realized one thing about this. In industry, they could care less if it came from Maxwell's equations or somebody just winged it and got it right. They wanted accurate design formulas. That's the only thing they want. And so in industry, you can more or less not worry that much about how it was developed, but it has to prove its worth in the processing. And some of you guys are going to be doing this stuff for a living. So hear me on this. For Duroid board, Duroid board's expensive, very low loss. It's the best thing to use, but don't use it unless you have to use it. That means if you're up and around gigahertz, you need Duroid board. If you're at lower frequencies, hundreds of kilohertz, even about probably 250 megahertz, you can get away with that green FR4 board. Now, do you all know what FR4 board is, most of you? Duroid board, if I find a piece, I'll bring it down here next time. I don't know what happened to it in my office, but it walked away. Somebody probably used it. But those things, you should at least be aware of these things. Some of you are going to be building things, especially in senior design, Halloween. Getting all sorts of messages, politicians, local area Halloween stuff, all this, you know. Is there anything official at Auburn for Halloween? They got a party anywhere? I mean, sometimes they do stuff like that. Yeah. I don't know. I mean, I'm not part of the student side, so I don't get all the stuff you do, but I do find out when there's an activity I need to be aware of because of parking talks. There's nothing, right? So okay, good. So anyway, you don't have to know these, but you should at least be aware of these are some of the formulas that we use in the design process. And typically, there's one other thing. Now, can you think of one of the constraints when we talk about transmission lines back in EMAG 1? What is the difference between a straight piece of wire and something that could be viewed as a transmission line? Yes, but the length has to be greater than 1/10 of a wavelength. Do you all remember that? So for these things, this line length, if you think about this, we had a length of line here. when we start talking about transmission lines, this is greater, this length, than lambda over 10 for it to be viewed as a actual transmission line. If it's not, it's just a piece of wire connecting things. That's, you gotta remember. Now, there's one other caveat to this, not just the frequency or how long the line has to be. There's a maximum operation frequency before this goes out of the transmission line mode. How many know what I mean when I say TEM mode? It's transverse electromagnetic. Now, if you have a standard coaxial cable, just think of a coax cable as such, right? If you looked at this, and I'll try to do this with a different color marker. If you looked at this, and you looked at the magnetic field lines, if this is the core, markers aren't all that cranked up to be. Alright, if you looked at the core of this, took a snapshot in time, you would see magnetic field lines that look like this. They would be wrapped around that thing. Y'all follow me? Right. The electric field that would go from the inner to the outer conductor would be like this. It's basically like this. These would be the lines that dictate the actual path the charge would take if it was being really moved on by the electric field. Both the electric and magnetic field are orthogonal to the path of propagating energy. Do y'all follow me? That's called transverse electromagnetic, TEM. It's TEM mode. Over here, you will have a TEM mode if the wave, if this transmission line is operating correctly. You basically have contours like that of a magnetic field, and the electric field would be doing this, and he shows some of this in the book. However, there's a maximum frequency that you can operate these things at before they go out of the transmission line mode and they start acting like a waveguide. And that's where signals are actually bouncing down. Alright? And that maximum frequency, he gives a crude one. The maximum frequency is going to be equal to, it's always proportional to C. And then the way he does it in his book, he uses epsilon relative, not epsilon effective. So he has C over 4H. And then it's equal to square root of epsilon relative. So that's the frequency, the maximum frequency of operation. I want to put something in perspective here. Now when you think about that, it doesn't mean a whole lot. Let's do this a little differently. So you know wavelength is basically velocity, which is C over the square root of epsilon relative. That's velocity over F. Y'all agree with that? The velocity over frequency is wavelength. Correct, class? Fine. Take a look at this. That means F max here, right? If this is going to be F max, I'll put it over here, is equal to C over epsilon relative, right here, divided by the wavelength. Now, we're going to put it over here so you can see this. So that's C over square root of epsilon relative, right there, wavelength. Now, I'm doing this for a reason. I'm trying to show you this in terms of wavelength. Remember, that's the maximum frequency, which would mean the minimum wavelength. Think about it. All right, now what do you notice here? I can forget about C, right? I can forget about epsilon relative. It means the wavelength itself can only be 4 times the height. Y'all follow me? It's a quarter wavelength thick. When it gets to be anything larger than a quarter wavelength thick, it starts acting like a waveguide. You got me on that, class? That's the way I think about these things. I mean, you can use this formula that he has in the book, but I always think about anytime that dot, or anytime this right here gets longer than a wavelength. In other words, the frequency goes to a point where this is longer than a wavelength, or longer than a quarter wavelength in free space, then I know I got a problem. I've got multi-modes, I got other problems. Okay.
And with those modes kind of bouncing
Yes.
dielectric there.
Here's what actually happens. Remember, that's copper on the back. That's copper here, all right? It'll be a very lossy waveguide, which what happens, the energy is going to try to ricochet back, but it'll spray off into space. You'll lose a lot. So that's the maximum frequency of operation that you can get away with on these things. By the way, that's very high. If you think about this, these thicknesses, just think about it. It's a couple of millimeters, all right? Think about that. A couple of millimeters. What's a millimeter wavelength? Think about it, all right? C over F. If it's 300 megahertz, it's 1 meter, right? If it's 3 gigahertz, it's what? 10 centimeters, right? 30 gigahertz, 1 centimeter. you're basically up there at basically optical kind of frequencies, actually just a little lower than optical. So most of the time you don't even worry about that upper max, but you need to be aware of it if they're thick boards, especially if you're using high power microwave energy, because then you got to be real careful not to get too near that maximum upper frequency. Y'all with me, class? All right, that's exposure to why we do what we do with these boards. And we basically do microwave engineering on small little things with a lot of chips. You guys work around ASIC chips, microcontrollers, stuff like that, right? How many have worked around an ASIC chip? Microcontroller. All right? I mean, don't you have to build things with chips in some of your labs? I think you do. All right. You've been around the block, you know what they're like. Well, you've got a whole bunch of these little components you're going to be mounting, and they're going to be working, some of them at least, at microwave frequencies. So the way you get around a lot of really expensive stuff like coaxial cable hooks and that is using microscope. That's the real goal. It's cheap, effective way to do this. Now, with engineering it, here's where the fun begins. We have to go back to the old Smith chart, but this one's going to be a rotated Smith chart. So I like to do it this way. I sent you them. I should have had you print them off or bring some. But be very attentive here. This gets confusing quick if you're not. It's not hard if you pay attention and see it and ask questions if you don't. But it gets to be very confusing if you're going to try to cram this thing Thursday night. You're going to really have trouble. It's not in a good way. All right, so you all know what a Smith chart is, right? It's basically something we use to do a lot of really transmission line work, but it is not in any way, shape, or form like something you have to worry about recreating mathematically. It is just a trajectories of the reflection coefficient. That's all it is. So when I do a Smith chart, I freehand them like such. That's my Smith chart, and then I put the equator in. I always do that. And then I find the center. That's the point I want to get at with any type of impedance matching. Then I show my R equals 1 circle. So this is R equal 1. After that, I make a few points. This point is also going to be 0, and this point is infinity on the edge. Y'all remember this kind of? All right. Then you have something right up here. This is J1, and this is the south pole minus J1. They probably don't like me saying this in the physics department, but that's basically the way it is. You basically have something that looks like the Earth, and you have a north pole that's plus J, a south pole that's minus J, and now after that, we can go ahead and start creating circles. If we have anything with a normalized impedance greater than 1, it's in here. This would be like R equal 3 maybe, something like that. Then over here, most of this are just trajectories that do this, and these circles just open up, right? That's what you're used to. Here's the difference. A rotated Smith chart, please hear me, simply takes this R equals 1 circle and it pivots it and rotates it right here. So you get the same exact circle, but this is called the rotated 1 circle. And you're going to see why it's important. Y'all follow? That doesn't appear on a normal Smith chart. Now, if you, I see you got the one I mailed. How many have seen one I emailed? You printed it. You're smart. You're way ahead of me. Okay. Those things will allow you to do all sorts of neat engineering tricks without a lot of crazy math. And some of the math does get a little crazy. So now we're going to show you how we use this. The first thing you do, and we're going to use this for matching, so let me just draw the basic circuit over here. You're going to have something over here, some Z load, and you're going to have some characteristic impedance here. And what we want to do is match the Z load to this. Ideally, Z load would be Z naught, and you wouldn't have to worry about it. But it's not 99% of the time in the real world. And Z load is also a function of frequency, remember that. So when we take a look at this, we're going to add elements. We're either going to add series elements and then parallel elements, or parallel elements and series elements. Now, the way you did matching back in the day was you either put a shunt stub or a series stub. Do y'all remember that? All right, you also did something where you matched, I think you did it with elements too. How many had me for EMAG 1? You did it with elements, if you remember, all right? Now I'm going to show you something. This is called L-section matching. The goal is to not have to have any kind of length of line. We're going to put all these elements right next to the load so we minimize the use of space on that board. We want everything up snug. We don't want anything any distance apart. But the thing you got to remember, this is only at one frequency. This is not wideband matching. That's a completely different animal, and that's something we don't even take up in this class. But this is going to be for narrowband matching applications. So we start by saying the first case is if we have the normalized impedance, which is capital ZL over Z naught, and this would be inside the one circle. Now please hear me on this. This is important to listen. You don't mess this up. So here's the one circle. If we have any kind of impedance that's inside here, say it's right there. Y'all follow me? I got a value that's going to be inside the one circle. It means the real part is greater than 1. Y'all follow me on that? It doesn't matter what the imaginary part is. It's somewhere in here. Now, when I do impedance matching, what I'm going to be doing is adding elements that don't waste power. I'm either going to add capacitors or inductors, and they have values of JX or minus JX as far as their impedances. What that means is, if you think about this, I can add or subtract J and move anywhere around this circle. You all see that? By adding it in series, I can move and I can be anywhere on that circle, but I can't get to this circle. That's where I want to go, because then if I can get to there, and I get rid of the actual impedance, I can get there, and that's where I want to go. This is the point. We want to go right to the center, because the reflection coefficient is 0. You all follow me on that? That's the goal. So, if we're inside the one circle, no matter what we add in series, we can't get to this circle. You all follow me? So we go to the opposite point. We go to the conjugate point, which would be Y. So if this is my ZL normalized, this would be YL, which is 1 over ZL. Y'all follow me on this? Alright. If we're inside the one circle, we're going to the admittance domain. Now, admittances you add parallel. Y'all follow me, class? Alright, so if I'm over here, now, just pay attention. You remember these trajectories for the real part are going to look like this, right? Right? That's the admittance. I can add minus J something and get to this point, or I can add plus J something and get to that point. Y'all follow me? Now, why is that important? Because if I get to this point or that point, and I go back to the impedance domain, I'm right on the rim of the one circle. Then I can add impedance and get right back to the center. Think about that for a second. The goal is to get to the center. So now, let me just show you how this works. And we'll do some real examples. We're going to do an example in a second on this one. So, for this one, I said, I'm assuming that normalized impedance is in the one circle. Anything I add in series won't help. I have to add in parallel. So I'm going to add a parallel element of admittance. It's going to have a value. I'm going to say it's positive. I'm going to add plus JB here to go from this point to the rim. Y'all follow me? So now I have JB that I'm going to add there. It's an admittance. Now I'm on the rim. Right here. And I know if I'm on the rim and I take 1 over that, I'm back to the impedance domain. And when I go from there, this would be point 1. This is the way I like them drawn when you hand them in to me, because I can follow your logic. Here's my third point. And now I'm going to move through here, and now I'm on the rim here. This is my fourth point. Y'all follow me? But when I'm on the rim, I know the real value is 1. It's 1. It's got a different J value, but this is always going to be 1, either plus or minus J something. Y'all follow me? That's impedance. If it's down here, it's going to be minus J. 1 minus J something, and I'll call it X. So now, what I need to do, if I have 1 minus JX there, I want to get rid of that minus JX. I'm in the impedance domain. I add a plus JX. Do y'all follow me? And I'll get rid of it. So when I come here, I just add a plus JX, and now I'm matched at that point. You all with me, class? That's the idea. I'm going to go through the whole thing with you in a couple of problems. That's if you're inside the one circle. We're going to start there. One thing you have to realize is, when we talk about adding admittances or impedances, they're normalized. You all follow? So I want to put this up here. Please write it down yourself too. Make sure you see this. If you have, and I'll do it this way, an inductor or a capacitor, when you look at the capacitor, or the inductive reactance, it's J omega L. The capacitive reactance is 1 over J omega L. This would be Z for these elements. Y'all follow me? Or 1 C, J omega C, correct? Now, if you normalize that, you divide by Z naught. Y'all hear me on this? You gotta normalize this stuff. So if you normalize this, then you would be dividing by Z naught, and I'll put that right here. Now these are normalized impedances. Y'all follow? Y'all get me on this one? Normalization means just dividing by the characteristic impedance. Now, when we select, and that's normalized impedances, the normalized admittances are 1 over this. So for this one would be minus J Z naught over omega L. For this one, it's going to be simply J omega C times Z naught. These are the normalized admittances. You with me? You'll notice they're functions of frequency as well as the values of the elements, C and L. Now, when I said I needed to find the value JB that would go from here to here, I literally have to take a look at what the reactive value is there, and I have to see how much I have to add to get that point. But that's normalized. So I say that this JB here, because I'm in the admittance domain, and here I'm adding positive admittance, right? Normalized admittance. Well, what's positive? It's this, right here. It's the capacitor. So I say that over here, JB would be equal to simply J omega C times Z naught, or I would say that the value of C, just take a look at that, would be equal to B over omega Z naught. We're going to do a problem. Y'all follow me? Now that's at a given frequency. That'll give me the value that I need for C. It would be in parallel. By the way, even though you're going to see some problems that don't. In the real world, you always use capacitors in parallel whenever possible. And you always use inductors in series, because an inductor in series doesn't block DC. A capacitor in series will cause problems. An inductor in parallel will act like a DC short, and those are problematic. Just hear me on this one. So capacitors, if at all possible, in parallel, inductors in series. Just remember that. You'll find some of the problems. So then for this one, that's normalized impedance, right? So, and if I wanted a positive value, like if you're down here, if you have minus Jx, then you want to add a positive Jx, which would be what? An inductor, right? So it would be this right here. J omega L, or basically this Jx, would be equal to J omega L over Z naught. So you could say that L is what? Well, L would be equal to X times Z naught over omega. Y'all follow me on that, class? Now, we're going to do a problem with that. Before I do one, I want to mention that's if you're inside the 1 circle. It means adding any series element, you can't get to the outer, to that R rim of 1. But what if we're inside the rotated circle? A rotated circle. This is an impedance. Now think about that. Here, we can add a series of impedance and get to this rim. And the minute I'm at that rim, I can go to the admittance domain, and I'm over there. I'm on the other rim, and then I can add admittance to get to the series point, to get right to the center. Which means the first element would be in series. The second element would be in parallel. Here, for this one, we basically have the first element's in parallel. It's a high impedance. Basically, you're inside the 1 circle, so we have to add something in parallel to get it down, so we can add something in series to get rid of the imaginary part. Does this make sense to you guys? When we do a problem or two, you'll see. And if you happen to be outside of both of these circles, then you can do whatever you want. We'll do that too. Those are the nice problems. You can add either series or parallel first. It doesn't matter. So let's take a look at some of these problems. And if you have a book, you know, look, I'm going to do a problem. I'm going to do an example out of his book, but we're going to do a bunch of problems. So, by the way, other extra quizzes aren't collected. I don't want to forget. You don't want to bring them up. this is, what I'm gonna do is example 10.2, page 551. He has an L section, he has a load of 250 minus J 250 into a 50 ohm line. That's gonna be a little tougher than I like, but we'll do it. So I'm gonna erase this and we're gonna do that problem. If you have a straight edge and a compass, and you have a Smith chart, or a rotated Smith chart, you can actually do this with me. But I'll show you the steps.
What page is it? 551.
I'll leave that up there. So this one, we have a load of 250 minus J, is minus J 250?
Yeah.
So, 250 minus J 250 is the load, and the characteristic impedance we have over here is 50 ohms, right? 50? Okay. Alright, well it's gonna be a tight circle to see. So now I'm gonna freehand this, and if you can follow along in the book or not. It's R1. So I come over here, first thing I have to do is normalize this. So my ZL is 250, Z naught is 50. So I find normalized ZL 250 minus J 250 over 50. Well, that's 5 minus J 5, correct? All right, now we plot that. And this is an estimate. If that's 1, let's see, 2, 3, 5 is probably right about there, but I might be a little big, all right? That's the real value is 5. For J5, it's somewhere over here, if you look on your switch chart. So it's somewhere about here. That would be my normalized ZL. Can y'all follow me? That's 0.1. Got that? That's inside the one circle. We all agree.
Yes.
Only thing we can do now is we've got to go to the admittance domain. So this was equal to 5 minus J5. We take 1 over that, and if you have your calculators, you can give me the exact value. And this is going to be 1 over 5 minus J5, which looks like 0.2 plus J.2. You can correct me if I'm wrong. Is that what he has in his book? Just do it if you've got a calculator.
I got 0.1 plus 0.1.
0.1, sorry, plus.
5 minus.
Huh?
Minus J5, right? Yeah.
There's 5 minus J5, right? So it's 1.1 plus J.1 when you take 1 over that, right?
Would the point you're in, would it be on the bottom side of the assessment chart, or like the bottom half?
What's that?
The first point.
This, oh, you know what? It's on me, you're right. That's absolutely right. I have this drawn wrong. It should be down here. It should be, this is plus J5, my bad. It should be down here. This should be 5 minus J5 right there. And that means when I go through here, that would be my first point. My bad, it would be here. And this would be 0.1 plus J0.1. And this, here's my one circle. Not drawn very well. Did you all follow me? So this is the second point. Now we've got 2 choices. I recommend you always add, because that's admittance, always add a capacitor in parallel. This is going to be a parallel element. You all agree with that, class? And we're in the admittance domain, so we're going to go from here. Now the real value is 0.1. So if you take a look at that one circle, it'll look something like this. But there's going to be a point here where you have 0.1 plus blank J that's going to be on the rim that you can look at. And if you look at his, would be 0.1 plus J.3. So we've got to go from here, and this is going to be J0.3. Can you see that on the rim, class? If you have access to that Can you find that point? Just look at the real value here. Here's, so you just leave it there. See the real value is 1. See where it intersects? It's 0.3. See it? All right, he's got this thing on his tablet. So that means we have to add J.2. Y'all follow me? I went from here, I want to get to that rim. That's my third point. This is second, this would be my third point here. That means we added J.3. But we started at J.1, so the actual value we added in parallel is J.2. Y'all follow me? So over here, I'm going to say I have to add J.2. That's the value in parallel. Got me? You guys back there, you all with me? Now we're right here. Now if you got your calculators, just do this with me. Now I'm going to go back to the impedance domain. From there I go right through the center there to here, and that's just 1 over that. So this value better have a real value of 1, and it's going to be minus J, I want to say 3, but I don't know. Can anybody do that for me?
1 minus
J3? 1 minus J3. So now we're here. We started here, 1, this is 0.2, that's 0.3, this is 0.4. Now we've got minus J3, we want to get rid of that, we add plus J3 in series. This is the impedance domain. So now here, I'm just going to add plus J3. And now, from that point on, I'm impedance matched. This will be a capacitor, this will be an inductor. We're going to get the values in a second. Everybody with me? Just be attentive here, because people get real confused because they're trying to fly through this without actually thinking deeply about it, and they miss so many things. Okay, so now we're going to get the values. He gives us a frequency for this, and I forgot what it was, but what is it operating at?
It's 800 megahertz. 800 megahertz.
800, I don't know why I chose that. It's high enough so microwave engineering will be useful, but it's not so high that we have to worry about the thickness of the board. All right, so we have that. Now, when we take a look at this, first element we have to add is an admittance, and we want J.2. That's the capacitor. Y'all see that? It's a capacitor. That means I say J.0.2 is equal to J, it's omega, so it's 2 pi times 800 megahertz times 8 times 10 to the 8, right? Times C times Z naught, which is 50. I can forget about the J's and stuff like that, and I can get C here would be equal to 0.2 over 2 pi times 8 times 10 to the, or 8 times 10 to the 8. Wait a second, 800 megahertz?
Yes.
Okay, that's right. And then it's going to be over 50. And you can give me that. That's picofarads, I think. 9. How many picofarads? Anybody? He does it. He has the answer in the book too, but I want to just make sure. What did you get?
7.9.
Pico, or you had 13?
0.8 picofarads.
Is that right?
That's what the textbook is.
Yeah. 0.8 picofarad. That's small. That's very small. It's almost too small, but that's what it is. So that's the value of the capacitor, right? Somebody want to tell me how to get the value of the inductor over here? Well, inductor reactance is J omega L, right? Normalized would be J omega L over Z naught. It's going to be equal to what? 3, or I can say what? I'll write it down here. J3, right? J3 is equal to J omega, which is 2 pi, 8 times 10 to the 8, 800 megahertz, J omega L, divided by Z naught, which is 50. So that means L itself is going to be 3 times 50, right? Then it's going to be divided by 2 pi times 8 times 10 to the 8. Now what do you get for that? This is a small inductor too, by the way. Anyone? 30 nanohenries?
Yeah, 29.8.
29.8. What is the book at? All right, now, I want to tell you one thing. This value right here That's small. If you're talking about values, sub-picofarad, you want a capacitor, the leads you gotta trim down way, they gotta be super short. If you have a capacitor that says on it, it's like 0.8 picofarads, and they do exist. Sometimes I can't believe it, but they do exist. If you wanna use that, the leads have to be as short as possible, because a lead that long, two leads that are probably 1.5 inches long, that's almost a picofarad right there. So you gotta be careful when you're dealing with that kind of stuff. It's very, did anybody have to use capacitors that were sub-picofarad yet? And anything? Your lab work would usually microfarad. Picofarad is ridiculously small. And you breathe on it, it'll change. That's how I feel about that. Okay, that's a simple one. That is for doing, it's called L-section matching, and this is for strictly something that's inside the one circle, right? So normalizing feeds. Now we're gonna do one where it's gonna be inside the rotated circle. If it's inside the rotated circle, your first element is in series. And it can be an inductor or capacitor. I prefer an inductor if at all possible. Series elements, always inductors can help. So now we do a problem with that. Okay. Now this is something a lot of times the confusion lies is over here. Remember how I did the normalized stuff? Always start with the impedance of the element, either capacitor or inductor, then normalize it. Divide by Z0. That's the normalized impedance. The normalized admittance is just 1 over that. Please keep that straight in your head, because that's where mistakes we usually make. So here, we're going to go to the next problem. I think it's the next example. And that's the rotated circle. And for the next example, what was book? So, what is it? Okay, so he says he's got a 10 ohm load to a 50 ohm line. This is an interesting one. So here's his deal. He's got a characteristic impedance here, Z0 equal to 50, is that right, 50 ohms? Right? And then over here, he's got a load of 10 ohms. This is kind of an odd one. There's no imaginary part to this. Do y'all follow me? We want to do a matching network before. So, our first step is to find ZL. That's 10 over 50, or 0.2, correct? So now we plot it. Well, 0.2 is right about here. If you look at this, this is going to be 0.2. Can you all see that, class? Just make sure you can locate that. That's 0.2, that's the big trajectory. It's inside the rotated circle. All right, now we have two choices. Remember, this is impedance. That's impedance. We can move this way, which would be adding a plus J impedance, which is an inductor in series. Follow me? That's preferred. Or you can move this way and get to that circle by adding a capacitor in series. That's minus J over max. Follow me? I always say, and I hope he does it, to use an inductor in series, if at all possible. So I'm going to move from there to there. So this is my first point. My second point is going to be here. Can you tell me what that value is? It's 0.2. See where it intersects. It's going to be like 0.4. Is it J point what? All right, so this is going to be 0.2 plus J 0.4. Is that right? Can you all see that there? Take a careful look on this. Do you have your books, guys? Can you all see it? Okay. I mean, you won't be able to tell on that, but just get an idea. Alright, so if you look at this, that means I added what? I added J.4 here, correct? You with me? You had J0, I added J.4, this is in series, so this is J0.4, it's a series element and it's an inductor. Now I'm right there. Now take 1 over that, and I better be at 1 minus J something. What's it, 1 minus J? Oh boy. Almost afraid of this. Just take 1 over 0.2 plus J.4.
1 minus 2J.
1 minus J2, 2J. Alright. Now, we want to add something to that so we get rid of the minus J2, so we're right here dead center at the end of the decay. So we're going to add plus J2. Y'all follow? And that would be what? That was impedance. This would be a capacitor in parallel, correct, class? Y'all follow me? We were at impedance, we add an inductor, we come to this domain, we're admittance, it's in parallel. Now we're going to add a capacitor that has a value of plus J.2. So here, got a capacitor here of J2. Follow me? That's admittance. Now we're going to get the values. But does everybody follow the thought process? The whole idea is just adding things, so eventually you get to the center. That's it. Alright, so for this one, this is an inductor, we had J0.4 is equal to the normalized inductive reactance, right? That would be J omega L over Z naught. I put down the formula just so you see. I think about it this way. Then I'll add the other values. I want L. So L itself is equal to 0.4, right? Times Z naught. Z naught is 50, I think. Isn't it? 50. Then it's going to be what? Divided by omega, correct? And I'll put the values in. So I have 0.4 here times 50, and then it's divided by 2 pi. Is this one at 800 megahertz too?
Is that 1 gigahertz?
All right. So 10 to the 9. So give me the value of L first. We just about made it on time. Just let me finish this example. No. What'd you get?
It's about 4 nanometers.
49 did you?
4 nanometers.
4 nanometers. Okay. Is that in the book? 4 nanometers. What about the capacitive reactance right here? Well, capacitive reactance is 1 over J omega C, right? When I normalize it, I divide, so it'd be 1 over J omega C Z naught, admittance is 1 over that. So I can say that J2 would be equal to J omega C, right, times Z naught, or I can say that C is equal to 2 over 50, that would be the impedance, and omega naught is going to be 2 pi times 10 to the 9th. So what do you get for C? What is this picofarad to it? Okay. What do you get? 2 times 50 is 100, so that's going to be 10 to the nice little 11. How many picofarad?
I get 6.3 picofarad. In the book it says 8 picofarad.
He did the opposite method.
Oh.
What did he do?
He might have done the. He has inductors in parallel.
Don't do that. Don't do that. Don't put it in inductor. Don't worry about it. That is another possible solution. What he did is go this way first, then up here and this way. That's what he did. Don't do that.
That's not 4 nanometers, that's 3.2 nanometers.
Yeah.
Is this 3.2?
Yeah.
Thank you. Does he do this also? 3.2 now? And what's this value for this?
6.4.
Picofarad?
Picofarad.
Now that's the way you do it. Inductor in series,
Yeah.
capacitor in parallel. If he did it the opposite way, does he do the other solution too?
He has the answer for it, but I don't think he worked it out, but it's the same.
Okay, don't do it that way. Don't put inductors in parallel, capacitors in series. Bad. I'm just telling you that. Personal experience. Okay. Now, finally, I'm just going to say this. If you have something that's not in either one of these things, if you're out here, doesn't matter which you add first. Let's say you get an impedance out here, all right?
our goal is to get to here. Well, if I'm out here, and that's the real circle, here, like so, no matter what I add in series with it, I can never get on that one circle. All right, I just can't. So what I can do is, if I'm here, I can add something and get to this circle, the rotated, and that would be in the impedance domain. Y'all follow me? Then once I'm there, I go to the admittance domain and I add something to get to the center. But if you're outside, keep both of them. You always go to the rotated circle, and then you go to the other side to get to this. So we'll do some of those, but trust me, I think you'll see it. Remember those trajectories. You move along the real part of the trajectory all the time by adding or subtracting.